In spring 2023, the Federal Highway Administration, also known as FHWA, completed testing of a cooperative driving automation, or CDA, use case that has the potential to safely reduce travel delay at signalized intersections. Following the successful execution of Scenario A, which can be found in the description of this video, Scenario B was performed for additional verification of the algorithm's optimization capability. The objectives of this use case are for traffic signal controllers to safely optimize their timing plans based on surrounding traffic, and for vehicles to safely optimize their approach to the intersection based on those plans. The vehicles in this scenario are equipped with cooperative automated driving systems, also known as CADS. To achieve the goals of this use case, advanced algorithms are implemented in Karma Streets, which is connected to the infrastructure's traffic signal controller and allows for communication with vehicles, and in Karma Platform, which controls the CADS-equipped vehicles and can communicate with the infrastructure. At the beginning of Scenario B, 3 vehicles are stationed at approaches east, west, and south of the intersection. Vehicle 1 is west of the intersection. Vehicle 2 is east of the intersection, and Vehicle 3 is south of the intersection. While the starting positions of the vehicles in Scenario B are the same as those of Scenario A, the speed limit of Vehicle 1's approach was changed. Vehicle 1 plans to travel straight through the intersection following a speed of 10 miles per hour instead of 15 miles per hour. Vehicle 2 plans to take a right turn at the intersection following a speed limit of 25 miles per hour. And Vehicle 3 plans to travel straight through the intersection following a speed limit of 15 miles per hour. When the test starts, each vehicle travels toward the intersection while broadcasting their status and intent information. The 3 vehicles simultaneously enter a configurable geo-fenced area referred to as the signal optimization range. Once the vehicles enter the signal optimization range, Karma Streets begins considering how to reduce the vehicle's average delay and plan future traffic signal phases. Since the speed limit of Vehicle 1's approach was lowered from 15 miles per hour in Scenario A to 10 miles per hour in Scenario B, the vehicles in Scenario B are estimated to arrive at the intersection in a different order than they did in Scenario A. Based on their speeds, location, and route information, Karma Streets estimates that if the 3 vehicles were to continue along their current trajectories, Vehicle 2 would arrive at the intersection first, Vehicle 3 would arrive second, and Vehicle 1 would arrive last. Unlike Scenario A, where it was most efficient to serve Vehicle 1 and 2 together in the same green light, in Scenario B, there is a significant difference in estimated arrival times between the 2 vehicles, so the algorithm recognizes that it is most efficient to serve them separately. The Karma Streets algorithm determines that it is optimal to give the east-west traffic signal priority first, since Vehicle 2 would arrive first, then the northbound traffic signal second to serve Vehicle 3, and finally the east-west traffic signal again to serve Vehicle 1. In addition, the algorithm understands that the vehicles will need to approach the intersection at a reduced speed corresponding with the order in which they will be served. Karma Streets uses this logic to calculate the optimal future traffic signal, phase, and timing, or SPAT plan, as well as the approximate times for the vehicles to enter the intersection. Karma Streets then converts that information into vehicle schedule messages and J2735 SPAT messages, and sends those messages along with roadway information to the vehicles through the Roadside Unit, or RSU. Karma Streets also sends commands to the traffic signal controller to implement the optimized signal timing plan. Using the received SPAT messages, the vehicles smooth their trajectories to enter the intersection box at their instructed entering times without surpassing their planned speed limits. As planned, the east-west traffic signal is scheduled to become green first, allowing Vehicle 2 to perform its right turn. Next, the northbound traffic signal switches to green just as Vehicle 3 arrives, allowing it to travel straight through the intersection. Finally, the east-west traffic signal switches to green again just as Vehicle 1 arrives, allowing it to travel straight through the intersection. This scenario illustrates how an algorithmic approach to cooperative signal optimization can provide mathematically optimal solutions to traffic problems, which reduce stop-and-go traffic, fuel consumption, and delay at signalized intersections while maintaining safety. For more information, visit the Federal Highway Administration's website at www.fhwa.dot.gov or email karma@dot.gov.